All right, so as opposed to a lot of you, like I'm mainly coming from purely machine learning background, and so here I'm gonna just be talking about like one recent technique in machine learning, in deep learning, called normalizing flows, and I'll just kind of lower my voice. Okay, so. Okay, so like normalizing flow, like why would we use them? So normalizing flow, they're like sort of a language for probability manipulation that's like useful for several things, like density estimation, generative modeling, and so like for example, like those images are like generated by like a normalizing flow model trained on a data set called celeb of faces, as you can see, and they can also like help for like Monte Carlo integration. So for example, like the Bayesian machine learning community also been using normalizing flows. So this is another application. So normalizing flow, they're based on this. Like the fundamental is like the change of variable formula. So for example, in 1D, if you have like a variable, a real variable, continuous variable z, scalar, and then you pass it through invertible function g to obtain like the variable x, then what would be like the density that x would be following? So if you take this density and you multiply by an elementary volume dx, then you obtain something of an elementary mass. I mean, I know I'm talking to physics people, but just let's roll with it. And so the change of variable formula is basically like a conservation of mass principle. And you just move terms around and you obtain like the change of variable formula. So that's like sort of a memento derivation that you can get from that. So it can be used for, as I say, density estimation and conditioning in MCMC. So like, for example, if you have like f, which is the inverse of g, then like you can have this formula to derive the density, the learned density on the X space. Like so. So it's like, so this is like the Gaussianization. It's like learning by Gaussianizing the data, for example. Another way you can use normalizing flow is for stochastic variational inference. So like you've seen some people here talking about like VAEs. And so instead of having just a linear transformation, just a diagonal Gaussian as your approximate posterior, you can use normalizing flow to make more powerful approximate posterior and hopefully have more performant models. Okay, so the change of variable formula, there's like already examples that you might already know, like this like scalar example, you have like a Gaussian with mean mu and standard deviation sigma, and that's equal like to the Gaussian density applied on the standardized version of the variable times the inverse of the standard deviation. So like if you look back at this change of variable formula, pz correspond to like the density applied to the standardized variable, and then sigma minus 1 is this like derivative term. And so like there's like this more general like example, which is inverse transform sampling, which is like based on the change of variable formula, and this is like roughly how you rewrite something that is actually kind of trivial, that like the derivative of the CDF is the density function. So now, like what happens when like you just move to like the multidimensional case, which is actually the hard case. The derivative, the absolute derivative part is like replaced by a Jacobian determinant term. And so this Jacobian roughly reflects like a change of volume. And so like once again, we're dealing with like density, which is mass over volume. So this is how these things relate. And so from here, like we can see several challenges like coming for like building these normalizing fluids to have model that have like tractable Jacobian determinant and a model that can be tractably inverted. So we're just going to see that with like a study case, for example, density estimation. So let's say you have like your data distribution px, and like you just draw an example from it. So like how you're going to try to learn a density model with normalizing flow is that you're going to map to the z space using, well, f of x equals z, right? And then you're going to compute like a p of z on this point x, and then you're going to add like the, and then, well, you do log of p of z, and then you add like the log Jacobian determinant, and that gives you like the density in the x space. So in this decomposition, there's like two parts. There's like this part in green, which is like the easy part because f is just like you're just applying a function, and then like pz is also like a density. It's a density that you can choose it to be as simple as you want. So here in this case it's a Gaussian, but it can be anything that you would find pretty tractable. Yes?
Just a naive question, but is there any assumption that this mapping f has to be, say, continuous?
It has to be it has to be continuous and bijective and differentiable. Yeah.
In this case, that doesn't seem to be the case.
It is. No, it's because like it's very like it's continuous, but then like the derivative is very it's very sharp. You know, like it's I mean, it's trying to approximate like something that is maybe very discontinuous, and so that's like I mean, it's like when you're doing a Fourier approximation of these like square waves. Like it's still as you approximate, it remains continuous, but it becomes more and more looking like this discontinuous square waves. Okay. Is that satisfying? Okay.
About the topologies, so why is this?
Oh, well, I can just imagine like if you see this horizontal line on the left plot, if I have a point an epsilon above and an epsilon below, then I don't think it's very continuous.
Yeah, it's continuous. Yeah.
Speed level.
Yeah, it's continuous in the strict sense of term, but it's like the derivative is very high in this horizontal line. Yeah.
Yeah, yes. Probably in a certain class of Lipschitz functions, you can probably represent some things that you can't. It's like you can write down certain two distributions that you can't represent with a certain class of Lipschitz functions, which is basically like the continuous formulation of something.
Yeah, so this is like, this function is like, I mean, if it's Lipschitz, it's like Lipschitz with a very high constant. So yeah, exactly.
Put this in a base with a lower Lipschitz constant.
Exactly, yeah, cool. So, okay, back to business. So we have like this part in green, which is like pretty tractable, pretty easy to compute, but then there's like this other part, which is like the Jacobian determinant term, which is actually like one of the hard parts. And so there's like two reasons for it. So like it's the Jacobian part for starters. So the Jacobian, like if you're in a high dimension, then like maintaining this Jacobian can be very expensive, both in computation and memory. And then there's also the determinant part, because like you're going to compute the determinant of a very large matrix, and so like naive implementation is factorial in the dimensionality. You can like have other implementation that are like polynomial, but like cubic. There's like other estimators that are like less expensive, but that have like much higher variance. I'm not going to talk about that in this talk, but so now like to try and like solve this issue, let's look at the matrices for which like computing the determinant like becomes tractable. And so there's like the case of simply like smaller matrices, right? Where like, well, having even a d factorial is not a problem. There's also like diagonal matrices where it's the determinant is the product of the diagonal term. And then like there's also like you can expand that to block diagonal matrices. There's also like other classes of matrices for which like the determinant is pretty tractable. So like for example on the left, it's, well, you can like now you can see it, but it's like a diagonal plus a low rank modification, and then you use the matrix determinant lemma to just reduce that to the computation of a matrix whose size is equal to the rank of this perturbation. And then on the right, there's like triangular matrices, which is like the diagonal matrices. The determinant, you can compute it as the product of the diagonal terms. And so, okay, so this is nice, but like maybe you want to have like nonlinear functions, like very powerful nonlinear functions. So how do we apply this, like for example, in deep learning? So one way to do this is like just stay on low dimension and have like this like invertible neural network with square invertible matrices, very small, and then like strictly increasing activation function. And then you can just invert the neural network like step by step directly, right? The fact is that like most model neural network architecture, they're generally like not built like that. They tend to have like feature space that are at least initially like larger than the input space. And so that's why like people have developed like neural scalar flow. So like if you stay on the scalar, like if you're using a scalar quantity, then like you can just have like an arbitrary neural network as long as you have strictly increasing activation function like previously, but also like strictly positive valued weight matrices. And then from that, you have a guarantee that your neural network is invertible. So then like you can also like look for example, for images and like exploit the convolution theorem for periodic convolutions, and then like basically like that it becomes an element, more or less an element-wise multiplication on Fourier space. And so why we're doing that? It's because like if we look at the weight in Fourier space, then it becomes something like a block diagonal matrix. And once again, the determinant becomes much simpler to compute. So another method that has been developed using neural network is something very similar to like a residual network, except they have like this bottleneck in the middle and some additional condition. But the bottleneck is important for the tractability of the determinant of the associated function, since like now we can use the matrix determinant lemma in a nonlinear setting to make the computation more tractable. Okay, so now another class of like generative model that has been like tractable before has been like autoregressive models. So like this is like a very simple elementary example of like recurrent neural network with Gaussian emission. So for example, you have an initial state H0 from which you create like a mean mu0 and a standard deviation sigma 0. And then you get like from Gaussian with this mean and standard deviation, you get x0 that you refeed to obtain your new state H1, and then you generate a new distribution, etc. So you can look at the reparametrized view of this model, where like you're actually having like these z variable at each time step that you're gonna conditionally modify linearly, right? Like you're just gonna add sigma 0. You're just gonna multiply by the standard deviation and then like add the conditional mean. And so then so that's like the generation, and then like if you look at the learning of this model, the learning of this model is also tractable. And why is that? If you look at the inverse, which is also like a conditional linear transformation, then the transformation of, for example, z3 will only depend on x0, x1, x2, and x3, but not on x4. So what does that mean? That means that like if you look at the Jacobian associated to this transformation, it's triangular. And then once again, if you want to compute the Jacobian determinant of this transformation, then it's simply the product of the diagonals. Okay. So, but like with recurrent neural network, like the computation is very like non-parallel, very sequential. Maybe you want to exploit your parallel hardware like GPUs, CPUs, And so that's why like one could build like a autoregressive model in a neural network setting, in a feed-forward neural network setting, where like you would mask the connectivity. So for example, like here at each level, you can have like groups of neurons, of nodes, that's going to be associated to each, one would call like each time step. And so then like each group of neurons will only be connected to preceding time steps here, right? And so if we keep doing that at each layers, like if we connect each group with all of the preceding groups of the previous layers, then we can guarantee that the Jacobian will have this triangular form, right? And then, once again, you can compute the determinant pretty easily. Okay, so like, then like if we apply like these restrictions to our models, to our like neural networks, then like if you look back at this at this problem, then we just like simplified our lives, right? Like the term that was supposed to be hard like became easy to compute. So now comes the time of like inverting a neural network, like which is the other challenge in normalizing flow. And so first of all, like why would you do this? And so the reason is that like once you train that density model, like once you learn to Gaussianize, well, you might want to generate from your model. And one way to do this is like to generate from the Gaussian base distribution that you have on the Z space, and then just try to reverse your process, right? And so like in our case, like, I mean, the case I'm working on is like, for example, like Gaussian noise to images, but it could be like from other vector space, right? So now like the question is, how do we invert a neural network? So in general, like we can't do this tractably. And so that's why like several like iterative inversion method has been developed. So for example, like bisection, which is like in the scalar case, which is like binary search by any other term. But that's not very efficient in like higher dimensions. So what other people have adopted, like for example in recent MintNet paper that has been developed recently, they've been using this root finding algorithm like to get like the inverse, the Newton-Raphson, and then they have like only a local convergence guarantee for their approximate inversion scheme. Turns out you can actually under certain circumstances get a global convergence guarantee. So if this is, so if you're using this kind of parameterization, so this is like residual flow developed in U of T, and that maps like from x to x plus f of x, with this kind of with this kind of constraints. So f here needs to be like contractive, so Lipschitz with a constant lesser than 1, strictly lesser than 1. Then if you use this iterative scheme, it will be guaranteed to converge to your solution to like x plus f of x equals y. But there are cases where like you can actually do the inversion tractably. So like in the scalar case, for example, like people have been using recently like piecewise simple function, and then you just need to figure out like where you are, which interval you belong to, and then you just do a simple inversion. So for example, piecewise linear or piecewise quadratic. And there's been recent work on like rational quadratic spline, so it's like piecewise rational quadratic. But in higher dimension, so in the autoregressive case, it turns out that you can, if you have like this, these conditional bijection, turns out you can actually invert tractably your autoregressive model, and that's like by having this just this forward substitution algorithm. So basically, like you just invert this each conditional like bijection sequentially. And so because of this kind of dependency, this has to be non-parallel. And when when you're in high dimension, like when you're in the, like for example, for an image 64 by 64 with 3 color channel, you end up quickly with something like 1,000, close to 10,000. So it's like not necessarily that practical. So I mean, if you contrast that, for example, with diagonal matrices where things are much more simpler, right? That's why like there's like been the development of like coupling layers, which you can be seen as like a very coarse autoregressive model, where you just like take your input and then like you just partition that into 2 parts, and then leave one part unchanged, and then like just do a diagonal linear transformation, a conditional diagonal linear transformation on the other part to to do your nonlinear modification. And then like when you want to invert it, it becomes pretty simple because like one part is unchanged and the other part it's a conditional linear transformation, so you can like invert a diagonal linear transformation. So like now turns out like when you want to like generate from our density model, then you can just use like this reversion process, right? Like generate from P of Z, and then like just do the inverse of F to obtain like the distribution of interest. Okay, so turns out that like each of these like normalizing flow have their own trade-offs and their own like architectural choice, and like maybe to not be too constrained by these architectural choices, one could choose like to compose these flows and maybe combine their strength. And what's nice with like combining those normalizing flow layers is that a lot of the desirable properties that you wish to have are actually conserved through composition. So for example, like inversion, right, for sampling, but also like computing the determinant, right, because the Jacobian of a composition is the product of the Jacobians, and then like the determinant of a product is a product for the determinant. So then, like for example, if you look at coupling layers which leave one side unchanged, which might not be great, like if you want to Gaussianize something highly not Gaussian, right? You can just combine those coupling layers to just like change the side that remained unchanged, and so on. Okay, so now like you can also use this the composition of normalizing flow to just try to appeal to the management of the bijectivity constraint. So for example, like if you have like a very high dimensional input vector, one issue that you may encounter is that you're gonna have like to carry on this like very large input vector because of the bijectivity constraint. But what you can do instead is like just apply a shallower normalizing flow on the whole input, and then like when the time comes to apply another normalizing flow layer, to just apply it on part of the inputs, and then like leave one side and once again like leaving a side unchanged, and then like repeat this kind of operation. So in this case, like the overall function is still bijective, because like the final input is everything that you've been discarding so far, right? And that you just need to concatenate at the end. But like for all useful purposes, you can just keep them where they are, right? And so like, I mean, what's interesting in this kind of design is that you can actually, like you just created here like a multi-layer architecture, right? So like, for example, I've been like applying this kind of multi-layer architecture in my real MVP work on like images. And so if you look at the feature that was created from these images, and you instead, like for example, decide to get rid of the lower level feature by resampling them, then like here the image doesn't change too much, but as you go up and up, like the image degrades in a certain way. So it's kind of reflects some kind of prior that we have imposed in our model, right? That also help computationally. So this is like sort of like the degradation that you would see in this kind of setting. And so I've like right now I've talked like I've been like faster than I expected. So I've been talking about like discrete time flows. There's other works on like the flow-based model that I haven't like mentioned yet, which is like continuous time flow, flows on discrete domains, and other like research in progress like adaptive sparsity structure and non-invertible flows. But we can talk about this later. So if anybody has like any question, just please go ahead.